Everyone. Hope all of you are doing well. So now all of us know that we have to go with the online teaching. So what we will do, we will have recorded lectures, and I will upload these recorded lectures on mostly on Mondays and Tuesdays, and then once in a week, which is going to be Thursday, we will have our online class where you can come online and discuss whatever doubts from the lectures and then from the assignments homeworks you have, anything which you want to get a clarification on, all that we can discuss. And we will not try to initiate anything new when we meet on Thursday. So lecture part will be mostly on Monday and Tuesday, and let's see how it goes, and then we can anyway, modify our plan in the later in this semester. Okay, so recall that what we had done in the previous week, we had started with the understanding that we are trying to define the notion of measure, and it should have certain desirable properties, and then we define the notion of outer measure, and we prove certain properties. Okay, so today we are going to continue, and we are going to discuss one of the important property, which was the additivity property. Okay, so we had already proved that subadditivity doesn't hold, correct? So now we will show that I'm sorry, I made a mistake. I'm saying, like, we had already proved the subadditivity property for the outer measure. Okay, so today we will discuss that this additivity property, namely that when you have disjoint sets and you take their union, the outer measure need not be the sum of the outer measures. Okay, so that is the additivity property we wanted, but we will see that outer measure does not satisfy this additivity property, and hence we lose on this desirable property. So then from here we will try to build on that how to get hold of this additivity property and define an appropriate notion of measure. Okay, all right. So yeah, this is one of the results which we will prove today. So yeah, let me see if I can also write something over here. Yeah, so at least I will be able to highlight. Somehow my iPad is not connecting to this screen. Anyway, so this is the property we are going to discuss today, and in fact what we will show is that there exist two sets A and B, for which uh, this property, this equation, the mu star of A union B is not as mu star A plus mu star B, and A and B are disjoint. Okay, so this we will show that existence of such sets. Okay, but before getting into this, let us recall that there are certain nice situations where uh, we could prove that outer measure satisfies the additivity property. For example, if you are working with the intervals, correct? So you remember that I had given some exercise. I will reiterate that, and yeah, okay. So what was this exercise? It says, like, if you have disjoint intervals. Okay, so here being intervals is also important. Then you have this additivity. Okay, in fact this is countably additive, correct? There are countably many sets here we are taking. So this is countably additive, but here having these intervals here is crucial. Okay, so similarly, we can come up with some other situations where the outer measure will satisfy the additivity property, and I'm going to discuss one of such situation, and because these kind of things will be used, the arguments which we will try. So basically, what the outer measure, if the set is nice enough, this nice enough has to be put in the commas, because one has to properly define it. Okay, so let me give you an example, like where for example, like, if you can somehow consider disjoint sets which are separated well enough, that means that there is a positive distance between them. Okay, so how do you define the distance between two sets? It's like this. So you look at the points x in A and points in Y, and look at their distances and take the infimum. So that is how you define the distance between two sets. Okay, so what we are saying, like, if these sets are not only just disjoint, but they are also separated by a positive distance. Okay, so you see, just disjointness is not going to guarantee this property. You can, for example, you can take interval 1 to 2 and then 2 to 3. These are open intervals. They are disjoint, but the distance is but intervals are not good examples, because for intervals we already have the property, but you can always write down examples. Okay, so think about that. Okay, so we are going to consider sets which are separated, okay, with a positive distance, and then we will see that the outer measure actually has the additivity property. Okay, so I'm going to give an example here, a particular one. So I'm going to focus on two compact sets which are disjoint, and then we say that the additivity property for such sets hold. Okay, but here I did not say anything about the distance between sets A and B. Rather, I assume that the set I am taking here is compact. Okay, so there's a small exercise here, that this hypothesis in this theorem, that A and B are compact and disjoint, this will ensure that the distance between A and B is strictly positive. Okay, so you prove this. Okay, this is like your calculus or from your real analysis. All right, so what we have got two compact sets, and we want to prove this equality. Now by the subadditivity, you already know that one side of inequality always holds, no matter which kind of sets I take, correct? So all you need to basically worry about is the reverse of that inequality, which is this one. Okay, so this is what we need to prove. In fact, in all the questions that we are going to attempt of this sort, only this inequality needs to be proved. Okay, all right. So as I said, the distance between them is positive. Let us call it delta. Delta is a positive number. Now we are going to basically apply the definition of the outer measure. Okay, and what does it involve? It involves that you cover these sets for which you want to compute the outer measure by a sequence of open intervals, correct? So what we will do is we start with an epsilon, and since we want mu star of A union B on the left hand side, so we start with that, and we can pick a sequence of open intervals, okay, such that this property is satisfied. Now this property we have used couple of times, since mu star of A union B, because A and B both are compact and hence the union is also compact. So this number here, whatever we have written over here, oops, this one should not, this is a finite number, and hence we can do this. Okay, so we can choose for a given epsilon an open cover which satisfies this. Okay, now we are going to make use of the fact that the set which we are working with is compact, and hence we can choose a finite subcover of it, because we have a cover by open intervals, so it's an open cover. Okay, and just for convenience, I will as earlier also we have done this, I will not write I suffix j comma jk, rather I will just denote them ij. Okay, and j is varying from 1 to some finite number n. Okay, this is just for convenience. You can rename these intervals that you have picked. Okay, all right. So now what we are going to do is, because we have a cover of A union B, so we have a relation with the mu star of A union B in terms of the lengths of these intervals, but then from here we need to pass on to mu star A and mu star B, okay, which will require that we work with covers of A and covers of B. Okay, now in doing this, certainly if we have a cover of A union B, we can always get a cover of, in fact the whole thing will also cover A and will cover B separately, correct? So but that's not going to give us what we want. So what we have to do is we have to make some choices among these intervals, so that we can get cover of A and we get cover of B in such a way that the between these two covers there is no overlap. If there is an overlap, then what will happen? There will be overcounting. Okay, overestimates will be there, but we cannot afford that, because we want to put mu star A and mu star B on the right hand side. So if we cannot try to put an extra quantity here, otherwise it will not give us the inequality that we are chasing. Okay, so what we will do is we will modify the sequence which we have started with, in such a way that we will be able to choose out of it covers of A and covers of B in such a way that between these two collections, they do not have anything in common. That means if an interval is covering A, then it will not cover any part of B, okay, and vice versa. So this is what we are going to do. So of course the original intervals are not going to do that, because we have absolutely no other condition on the intervals. Only this thing we know, that they cover this, and then the size is controlled by the mu star A union B plus an epsilon. Okay, so what we will do is, at this point B will make use of the fact that these guys are, separated. Okay, so this we are going to make use of this fact that there is a gap between these two sets. Okay, so now this gap will basically dictate that, okay, if I had a small enough intervals, compared to this delta, then they can only cover part of A or part of B. They cannot cover both. Okay, so that is what we are going to do. So we basically are going to decompose or subdivide each interval Ij into finitely many subintervals, because Ij is a finite interval. So I can always cover it with finitely many, again just put them open intervals such that their length is at most delta by 3. I mean, I can take any number small here. Delta by 3 is just sufficient here. You could have taken delta by 4, delta by 5, whichever you like. Okay, so this process you can do with every interval Ij for j equal to 1 to capital N. Okay, this finite cover. Okay, so what will happen, that we will get for each Ij, we will get these subintervals. Okay, so I am naming them as j suffix j comma k, and this will vary, this k will vary from 1 to some number nj. Okay, and this is the cover. This is going to be basically a cover of Ij. Okay, so j is varying again on a finite set. And what we will also make sure, because we will have to compare the sizes, so we will also make sure that the size of all these subintervals put together, it's not too large compared to Ij. So this is like at most an epsilon upon 2 to the power j plus 1 extra part here. Okay, because finally we will have to sum over j also. So we need to make sure that when we are summing, the extra part is not too large. So that is why this 2 to the power j plus 1 in the denominator. Okay, this can be done. You just draw a picture and then cover the any interval by smaller intervals, and making sure that the increment is very little. Okay, so this way what we get a collection which is indexed by j as well as k, and this is the cover. Okay, so when I cover of this union of Ij, and hence also cover of A union B, correct? So if you measure the sizes, you will see that this is basically going to give you the total size of Ij's plus these numbers which you had written here. But you see here I had written 2 to the power j plus 1, so let me correct it. So this is 2 to the power j plus 1. Okay, that is why you are getting this epsilon by 2 here when you sum them up. Okay, so we have got that the total size is like the size which is the originally we had taken, and then an extra epsilon by 2. Okay, but epsilon is anyway, I mean, as small as we want, so we will have no issues with this extra factor. Okay, so now what we have basically achieved, that we have got by these subintervals a cover of the union A union B, and this extra condition that the size of these guys is at most delta by 2. Okay, again, I mean, this delta by 2 is basically going to work. You could have made it slightly smaller also, that's okay. Okay, and now the point is, because each of these intervals, they are smaller than delta by 2, so what we can easily verify that these intervals cannot intersect both the set A and set B, correct? Because the distance between them is delta, correct? So if an interval is intersecting A, then to reach to this other set B, it has to go at least delta distance, but its total distance is delta by 2, so it cannot reach. Okay, so any two intervals which we take, so what we can do is, because of this, we can actually choose among these j suffix j comma k, we can choose subintervals which give us cover of A and similarly cover of B, and in such a way, so this is the cover, in such a way that these guys do not intersect. Okay, so this is possible because we have now reduced the size of these intervals. Okay, all right, And yeah, this is, so I mean whatever I just said, you can just verify that. Now just putting everything together, so the total lengths of these subintervals can be written in two ways. I mean, one, you first write the intervals which contribute to A, and then the ones which contribute to B. And now this guy will have a connection with mu star A, and this guy will have connection with mu star B. Okay, but since this is, I mean this part is equal to this thing, so what we have that from the previous equation, that this total is less than equal to mu star A union B, and then you remember there was an epsilon and then there was an epsilon by 2, so that is why this has become 3 epsilon by 2. So now just apply the definition of mu star A and mu star B. So mu star A is going to be less than equal to this first sum, and mu star B is going to be less than equal to the second sum, and we get this final inequality, correct? And as I told you earlier that epsilon is arbitrary, so you get what you wanted, correct? So what is the underlying idea here? The idea was like we could choose these intervals so that they intersect only one of these sets, while covering these sets, and this is basically a crucial point here. All right, so if we can make sure that the sets are sitting apart by a positive distance, then this whole argument is always going to work. Okay, so this is one sort of instance where you can always guarantee that the additivity property for the outer measure holds. Okay, so now we move on and prove a general result. Okay, that this additivity property does not hold in general. Okay, so here this proof is like more of a theoretical type. It is going to be like we will show that there exist two sets rather than giving concrete examples. Okay, so that's not really possible here. So what this proof, one has to go through it a couple of times. This uses this concept of axiom of choice. Okay, so what we will do is we will construct a sequence. Okay, we will construct a sequence of sets using this axiom of choice, and we'll show that if we had additivity, then we will get basically contradictions. Okay, so this is what we will do, and this is very typical. This kind of argument is used in measure theory. We will see like this kind of argument even later on. Okay, so I would suggest that if you do not understand in first go, try to rewrite this whole thing which I'm going to present in your own way, and try to go through it and discuss it like a couple of times to really understand what's happening. Okay, so what we do is we start with a set or this interval minus a to minus 1 to 1. You could have taken any interval, that's not really important here. So and then you take any point here. Okay, so what I'm going to define, basically I'm going to define an equivalence relation on this. Okay, so define this a tilde. This a tilde consists of all those points which differ from a by a rational number. So this is the notation for the set of rational numbers. Okay, so look at for any given a, look at a tilde, the set which consists of rational number, it consists of points in minus 1 to 1 which differ from a by a rational number. Okay, so basically this c, a minus c is a rational number, so this you can write this c as a plus or minus a rational number, correct? That is how we are saying. Okay, so now couple of small things which you can verify yourself, that if you take 2 points such that these a tilde and b tilde have something in common, then one should be able to see that a tilde has to be b tilde. Okay, and in fact so that this relation, that a tilde that a is related to c by this, that a minus c is in rationals, so you can show that this is an equivalence relation. All the properties you can easily verify. Okay, so I will not give you the complete details of this, because these things you can easily verify, and these things are the equivalence classes, and hence the set can be decomposed into these equivalence classes. Okay, All right. So this minus 1 to 1 we have basically expressed as the equivalence classes here. Okay. Now at this point we make use of this axiom of choice. So what we will do is we will uh, apply this axiom of choice and construct a set which we are calling as V. What is this V? Basically this consists of exactly one element from each of the distinct classes. Okay, so uh, this kind of choice is allowed or is guaranteed that we can make such a choice by the axiom of choice, so if you have forgotten these things, you should go back and read a little bit of your uh, uh, this course on, I think in calculus also you may have done, but certainly in real analysis when you are starting discussing the well ordered sets and so on, John's lemma, those kind of things. So you can go back and read or browse through those things and get hold of, like, how does this axiom of choice work and so on. Okay, so but right now we are just going to apply it, and we are saying that this axiom of choice is going to guarantee that we can make this choice, that we can choose exactly one element from each of these distinct classes and construct this set V. Okay, so in particular what is going to happen, that if I look at V intersection any of these A tilde, so this will have exactly one element, correct? Okay, and now certain things you can easily notice, that if V is over here, that is by definition of A tilde is like A minus B should be a rational number, correct? In other words, what we can do is we can write A as R plus V, where R is a rational number. Okay, so we will make use of this representation, and notice here this A is coming from minus 1 to 1, V is also coming from minus 1 to 1, so the range of this rational number will be in the interval minus 2 to 2. Okay, so that is what we are going to write next. But we know that the rational numbers, they are countably many. So in this interval, because this is where the rationals which will depend on A and B are going to lie, so we basically enumerate these rationals as R1, R2 and so on. It's a countable sequence, and we see that this interval that we started with can always be written like this, because any A I take, that can be expressed as R plus V, one rational number R and some V which is coming from the class or the set capital V which we have taken. So this minus 1 to 1, this whole interval can be put into the union of these sets R k plus B, because we have enumerated the rationals. So basically this is a countable union, isn't it? Now at this point you see that these sets here, they are translate of a fixed set. Okay, so you remember in the discussion on outer measure we had already seen that subadditivity holds and then translation invariance hold. So we use these two properties, subadditivity and translation invariance, to compute that measure of, or the outer measure of this interval minus 1 to 1, which is 2, is less than equal to the sum of the outer measures. Actually I should have written here mu star, I'm sorry. Okay, so this is like mu star, okay, because this is not an interval. Similarly over here, okay, so just correct this. So mu star, but the mu star of this guy, because this is a translation of a fixed set, is same as the mu star of the set V, and you see this is an infinite sum of a fixed number. Okay, so this guy, that means the 2 is less than equal to this sum, that means this mod V has to be positive, because if it was 0, so you see, I mean we did not have any uh, understanding that how does the outer measure of this V behaves. Okay, but we have got a relation which says that 2 is less than equal to the sum of outer measure of B, okay, this infinite sum. So that means this has to be positive, the outer measure of B has to be positive, because if it is 0, then we get 2 less than equal to 0, correct? And that would have been a contradiction. And for this B, there were only two choices. One is it is 0 or it is positive. So 0 is going to contradict it immediately. So the other possibility is that mod v is positive. Okay, so for that there is absolutely no issue right at the moment. If mod v is positive, we do not get any contradiction. Okay, so now we will have to basically show that even this assumption on v is going to contradict something. Okay, and then we have basically exhausted all the possibilities for v, and hence such a v cannot be constructed, correct? So this is going to happen when we really assume that the mu star is additive. Okay, so that is basically going to contradict the fact that if we assume that the mu star is additive. Okay, so some observations before we get into the final argument. So look at two distinct RJs, RJ and RK, and look at their translation by V. Okay, so we say that these guys should be disjoint, okay, or distinct. Okay, because if I take something in common, then that I can write it as V1 minus V2 has to look like RK minus RJ, but RK and RJ both are rationals, so their difference is also rational, and then it will tell me that V1 and V2 they will be in the same class, correct? But he has been constructed by choosing exactly one element from each class, correct? Each distinct class rather. So these V1 and V2 they have to be same. Okay, and hence RJ and RK, and hence these two numbers are or these sets are same. Okay, so they will be distinct always. All right, now okay, so now you see that RK is coming from the enumeration of -2 to 2, and thus B is a subset uh, inside -1 to 1. So when I put RK plus B, at most we will hit -3 to 3, correct? This interval, which is a finite interval whose outer measure will be length of this, which is 6. So now we are going to make use of this because each of RK plus B is contained over here, hence their union is also contained over here. Okay, now at this point, if we had assumed, because we have shown that RK plus B, these sets as K changes, they are disjoint. So if the outer measure had had this additivity property, then we would have got that for any fixed n, if I look at the union, this should have been exactly the sum of the outer measures. Okay, but again translation invariance will tell me that this is mu star b and it is being summed n times, so you get n times mu star b. Okay, so what we will actually get if you combine this one and this one, we will get that this number n mu star b is less than equal to the size of this, which is 6. But you see this n is in your hand, you can make it as large as you want. You can take 100, you can take 1 million, and you can keep on making it large and large, correct? So this is not possible because this is a fixed number. A fixed number times n is unbounded, correct? So it cannot be less than equal to 6. So why we are getting this? Because we assumed that the outer measure that you started with is additive. Okay, and mu star b is positive. Okay, because if it was 0, then we would have got a contradiction earlier itself. Okay, so this proves that this additivity is not going to be true all the time. We can always make sure that these sets exist, for example these guys. All right, so yeah, I mean, now I have some small exercises here for you, so you can think of it as a homework and then try to do within this week, and you can discuss all these problems when we meet. Okay, but you must try. Okay, so I stop here, and then we will continue in the next class from here onwards. Okay, all right.